So we're going to move directly on to our next one, which in fact is Timothy Newbold.
Hi, should I just go ahead and get started then?
Please do. Yeah.
Okay. Um, so I'm Timothy Newbold, a mechanical engineer here at Honeybee Robotics. Today I'm going to dive into our recent developments with our concentrated solar simulator for molten regolith electrolysis. Please continue. So just an overview and background on the project as a whole. This is a NASA-funded project, stands for Gaseous Lunar Oxygen from Regolith Electrolysis. Because lunar regolith covers most of the moon's surface and the moon has no atmosphere, the regolith itself serves as a prime candidate for oxygen to be removed from should we choose to build a habitat on the moon.
This one, I cannot hear
Can somebody mute themselves, please?
the audio.
Yukiko, I think you need to mute
I don't
yourself.
know. That's why switch audio and then okay, I can this one.
Thank you for that. To continue, the moon does not have an atmosphere and is mostly covered in regolith. So it serves as a prime candidate for oxygen to be removed from should we choose to build a habitat or base on the moon. So this research is critical to that. And if you could go to the next slide, we show how the regolith is about 45% oxygen by weight, meaning that about half of the regolith covering the moon's surface has the potential to be used for as breathing air for anybody that would choose to go and build a habitat on the moon. I show some of the chemical composition in two of the simulants that we primarily use to simulate both the Highlands regolith and the Mare regolith on the moon. I show this to indicate what we will assume to be the major constituents in the eventual slag after electrolysis, and to show that the smaller percentage end members are still important because during phase change and electrolysis, they can also become a part of the gas. So the gas is impure and would still need to have these elements processed out. If you can continue to the next slide. So to start, we first need to phase change the regolith and pre-melt it. So we had a few different heating methods that were investigated, both here and at Kennedy Space Center. We feel that a Fresnel lens or some array of would be the flight solution, because then you have no additional power going to the melt, and any power is only used directly to apply voltage to the electrolysis setup. However, testing on Earth becomes difficult due to the atmosphere and varying weather conditions. So as you can see on the lower right, that's a picture of the inside of the concentrated solar simulator that we've developed here. Utilizes a xenon short arc lamp in tandem with an elliptic reflector so that the point source of light is located at one focus of the reflector and the regolith bed is located at the other focus of the reflector. So then following these trade studies and this development, we proceeded to test and try to phase change regolith. If you could continue. And so then I showed the comparison both in open air, what a melt looks like using the solar simulator, and in a vacuum. We feel this is important to highlight because it shows how testing in open air, from what we've experienced, doesn't seem to give you the same results. The surface is much more well behaved due to the atmospheric pressure, and you don't have, it's more of a static environment versus the test under vacuum is constantly outgassing, bubbling, expanding, and it creates more of not a microporous structure, but a porous structure with some internal cavities. And then these potentially present some issues when you proceed to electrolysis and some that you would have to design out essentially. But just to show that testing in air is definitely easier than vacuum, and to show that the concentrated solar simulator works. So following these results and gathering the data on the temperature, viscosity, etc., we proceeded to attempt an initial electrolysis attempt. If you could, next slide. And so this shows in the upper right our electrolysis assembly, both before being pre-buried in regolith and then after buried in regolith and being used. So in the lower right, you can see once we removed and separated the electrodes from the rest of the electrolysis stand, you can call it. There are a few points that we wanted to bring out that we feel highlight that oxygen was in fact released from the regolith. The first being the oxidation on the electrodes tips. So this was left pre-buried in the regolith and allowed to cool under vacuum. So we assume that no or minimal outside oxygen would be present at these electrodes unless it was being released from the regolith at elevated temperatures. There's also the orange, you can see residue on top of the upper electrode in both the lower picture and the upper right that was not present in any of the previous melts. And we believe this to be the byproducts of the electrolysis reaction, namely the silica that I showed in the initial graphs and likely iron. That's why I brought up the lower percentage end members because those will likely become a part of the gas and potentially skew the reading that you'll see in this next slide. But with this data, we were also able to confirm a mass flow rate increase out of the chamber during electrolysis. So if you could continue. So this is some data from some initial testing that we had in a homemade thermocouple. I'm not sure if I mentioned before, out of platinum iridium. Compared to the control test, we know that we released a significant amount of oxygen. Like I said, because of the lower percentage end members that also become gas when volatilized or electrolyzed, we can't be 100% sure the quantity. But we're looking to make the test setup more robust and expand the duration for which we can operate a test. So hopefully we have specific answers to quantity soon, and we believe that this test indicates a successful release of oxygen, which should allow and is critical for getting humans to the moon and allowing a habitat to be developed or a base to be placed on the lunar surface. So I believe this very briefly covers all the recent developments that we've done. But if you'd like to know more, this kind of concludes my presentation. Feel free to reach out to Honeybee Robotics or to myself directly. My name is Timothy Newbold again. I just want to thank you guys for listening and thank you for your time.
All right, thank you very much. So we have a question for you from Matthias Sproul. Would inert gas atmosphere be a compromise between vacuum and open atmosphere?
Yeah, and we've, in tandem with this, I had mentioned that we are also investigating a cold walled reactor. So instead of doing this more ISRU on the surface, you transport regolith into a confined space that you can pre-purge with some inert gas. It is a consumable at the end of the day for flight, so that's the main compromise you'd be making and drawback. So you'd have a limited number of uses, and we're trying to minimize consumables by making this ISRU setup. But definitely possible, and we have given that some thought.
All right, thank you.